working on double integrals and rectangular coordinates. And you got lots of practice on this over the weekend. So let's summarize this. So the first type is looking something like this. You have two functions of x, y is a function of x, defining kind of the top and bottom. And then we're gonna go. Then we have x values, kind of starting x value and ending x value. So this is type 1, and we say, what do we say? We say bottom function to top function first, and then left x value to right x value. That's kind of our mantra. The mantra is bottom to top, left to right. That's type 1. Bottom to top, left to right. And the bottom to top, those are functions of x. And then the left to right are x values, right? The left x value, and then the right x value. And so bottom to top would be dy, right? dy. And then left to right would be dx. So the way we think of this is, you think of this, the bottom to top then can be anywhere in there. So anywhere in there, a typical slice like that, right? So a typical slice comes first from, in this case, from G1 to G2. And then we're going to say, where's the first one of those? Over here, left to right, right? So at the left end. And then we're going to think about accumulating all those kind of strips across to the rightmost, right? So first, well, that's there. So first, bottom to top, on any typical place in the whole region, and then left to right. We start at A all the way to B and accumulate across those kind of vertical strips. Okay, then type 2 would be something like this. Type 2 is then what? A left function, and then this is x is a function of y, to a right function, and then a bottom x, y value to a top y value. So the mantra here is left to right, bottom to top. Left to right, bottom to top. So left to right means a typical strip. Everyone watch. Any typical strip like that. Anywhere. That's our left to right. And then we're going to look at accumulating all those kind of strips from the bottom all the way up to the top. Didn't get a chance to finish that animation. So what I wanted to show was those horizontal, kind of a typical horizontal strip, building up from bottom to top. Now the type 1 and type 2, that's just our language, so we have some way to talk about it. But for instance, on the exam, it never says type 1 or type 2, okay? It never uses that terminology. Okay, that's just for to make it easy when we're conversing about it. Okay, but this should be very familiar. That's just a summary. If you, with the great success you had in the web work, I looked at the web work statistics, and there was great success and very few questions to me on email. So I'm assuming that this is just a summary review. That it's nothing new. Any questions on that? So what we're going to do is you're going to do 4 problems. And you're going to do these all in your notes, okay? And then in about 20 minutes, I'm going to tell you which one we're going to transfer to the blue sheet. You're not going to have much time to do the transfer, okay? It's just going to be copying over from your notes, okay? So that each of these double integrals indicates a region in the xy plane. The first thing you want to do is sketch that region, okay? And that should go without saying, right? This is always about a visual of that region based on the boundaries, okay? So even if I didn't say sketch the region, that's just what you would do to solve these problems. You would sketch the region, but I'm going to just emphasize it. And then based on the region, then you're going to start over, change the order of integration. So if it's a type 1, make it type 2. If it's a type 2, make it type 1. Okay? Changing the order may or may not result in one integral. Okay? So you may be able to do it in 1, or you may need 2. So there's no guarantee on any of these, 1 through 4, that you're going to get one double integral. You might have to do a sum also when you reverse the order. It's type 1 or type 2, number 3? Type 1. So the functions are going to be functions of x, taking us bottom to top first, and then left to right. So from 0 to x plus 1. So we'll just sketch x plus 1. Like that. And so 0 to x plus 1 is going to be something like from the y-axis up to x plus 1. And then where does that happen? From 2 to 4. So starting on the left at 2 to 4. Okay, so I'll use blue here. So that first integral would be this right here. That's the first integral. Okay, and then I think this point here is this 4, 5? And does 4, 5 go through this other function? So now we're going from 0 to negative 1/2 x plus 7. Okay, so that has a y-intercept of 7. Like this, and then does that go through the point 4, 5? 4 times negative 1/2 is negative 2 plus 7 is 5. Okay, so it has a rate of change to negative 1/2, y-intercept 7. It's going to go like this. Okay, so the second integral goes from 0 up to that, bottom to top, right? Bottom, 0 to top, and then left to right, starting at 4. Well, lo and behold, it starts at the intersection to 14. And where are we at 14? 0. So 14 is right here. So from bottom to top, 0 up to negative 1/2 x plus 7, but left side 4, right side 14. So the second integral is that right there. Questions so far? So now we want to change this to type 2, which is going to go left to right and then bottom to top. So what do we notice about that? So the boundary of this whole region is like this. Okay, there's the boundary of this whole thing, right? So what's the left side of this? What's the left side? We're going to go left to right first. What's the left side?
2 and then it changes.
Is it 2?
No.
Is the left side 2? Partly 2, right? So at the bottom of this thing, the left side is 2. But at the top of this thing, the left side is this function, right? This line. What does that mean for us? What does it mean for the solution to this problem when we rewrite it? You're going to have to split it up, right? So because the left side changes, the left side down here is 2, but then the left side is this line, it's going to change right there at that y value. It's also going to be a sum of double integrals when we write it, when we change the order. Okay, so we'll do the lower half first. So the lower half is going to be what? Left to right, 2, 2. So we need this function. So this is y equals x plus 1. So therefore x equals y minus 1. That's this one up here. And this one that was y equals negative 1/2 x plus 7. What'd you get? Negative 2x plus 14 is what I'm hearing. 2y, thank you. So now when we go left to right, these will be our functions. X is a function of y. All right, so we're home free now. We're gonna at the bottom. We're gonna go what from left to right. So that's the function just what x equals 2, all the way to x equals negative 2y plus 14, and that from bottom to top. Bottom is x equals or y equals 0 to. Is this the point 2, 3? Yep. So 2, 3 is that y. This dividing point is y equals 3. So from 0 to 3. So that is this thing here, right? And that's dx dy plus. So now we're going to do this top part. Again, left to right, bottom to top. Left side is x is a function of y, right? Left is y minus 1. To right is our negative 2y plus 14 again. It's the same right side for the whole thing, right? It's the same right boundary for the whole thing. So we're going to go y minus 1 to negative 2y plus 14. And it's that left to right for what range of y? Bottom to top. So it would be from 3 to 5. How many had it before I started? Got it right? How many had most of it before I started? Questions? Does it make sense? Anybody have a question on that? Can I erase? Going once. Gone. I'm a tough auctioneer. Okay, here we go. Next one. So now, is this type 1 or type 2? This is type 2 because dx dy, meaning I'm going from left to right and then bottom to top. So this is, you gotta think, this is x is 1/2 y and x is radical 25 minus y squared. So x is 1/2 y is the same as y equals 2x. Something like that. Okay, and then x equals square root of 25 minus y squared. So if this isn't familiar, make it better be familiar really quick. Okay, because we're going to see this kind of thing a lot. X equals radical 25 minus y squared is what?
Semicircle.
Semicircle. Which side of the semicircle? Which half? Top half? Right side, right? X equals radical 25 minus y squared is for positive x. That's going to be the right side of the circle. Okay, so, and with radius? 5. Okay, so now we're going from left to right. To the left side is our line, and the right side is the circle. So to the left of the line, and then the right side is, sorry, left to right. So the left boundary is the line. So to the right of the line, and then the right boundary is the circle. So it's going to be something like this, and then that outer integral will tell us bottom to top. So the bottom is 0 up to 2 root 5. Is that this y coordinate right here? Okay, so this is the coordinate pair. Is it radical 5, 2 radical 5?
Yep.
So you should be able to find that intersection point by setting those equal. When you square and solve for it, you should get y equals 2 radical 5. That makes x radical 5. So we're going from, so the bottom is 0, the top is the 2 radical 5, the left side is the 1/2 y. So clearly we have this region right here. And now we're going to change the order of integration. And we're going to go do type 1. So questions on the region? Are we good on the region? So now, when we change the order of integration, what's the bottom? We're going to go bottom to top, right? So what's the bottom of the region? 0. Just one bottom, or more than one bottom? It's all the way across. All the way across this region, it's 0. What about the top?
There's two different. We have two different ways to get there.
Okay, there are two different functions that create the top of this region. Do you see that? On the left side, the top is 2x. Over on the right side of the region, the top is
Negative root x squared.
yeah. So we have a typical strip there, and then we have a typical strip over there with different tops, right? Different tops. So again, we're going to need the sum. Now we know that the bottom is always 0. So the top over here on the left side is 2x. And that part of the region is from
0 to root 5.
that's this here. It's going to be our first double integral. What I've shaded in red, that's going to be from 0 up to 2x. And then left to right. Left side is 0, right side is
Root 5.
x value radical 5. And now we're doing dy dx. Okay, over here on the right,
0 to negative root x squared plus 25.
so it's going to go from 0 to,
Negative square root x squared plus 25.
so now we need this circle as y as a function of x. So that circle as y as a function of x is just y equals, why are you saying negative? Is it negative? Okay, so what y equals negative square root is the bottom half of the circle. Y equals positive square root is the top half. That's what we have. We have the top half. So it's positive square root of 25 minus x squared. And that's from what to what? Left to right. Left side starting is? That's our square root of 5. 2, 5. Questions on that? All right, so sketch and do number 2 on your blue sheet. Copy it over. You got 2 minutes. Number 2 on your blue sheet. Okay, so we got it written down. So this last one, number 4, so we saw it as I gave it to you as a type 2. We did it as a type 1. But there's actually a whole nother way to do this that's a lot more convenient for this region. So looking at a circle here with center at the origin, and then up to this line. Do you see another kind of paradigm here or another approach? Yeah? Yeah, a lot of you are saying it. Okay, so yeah, polar coordinates. Remember polar coordinates from Calc 2. Polar coordinates is based on, rather than x and y, right? Rather than how far you are left and right and how far you are up and down, it's based on r is distance from the pole, which we used to call the origin, and so the pole is right there, distance from the pole, and theta, which is our standard trig angle, right? It's the angle swept counterclockwise from the positive x-axis. That's our standard trig angle. Swept counter, so 0 is the positive x-axis. We're sweeping counterclockwise from the positive x-axis. Okay? So rather than, bottom to top, left to right, bottom to top. So now we're thinking, what? Inside to outside. So it's kind of like our strip is like this. So inside to outside, and then starting angle to final angle. So imagine our first step is going to be what? dr. Going from here out to here. And that would be anywhere. And then we're gonna accumulate all those, starting at theta equals 0 up to theta equals. So what theta is that if it's y equals 2x? No, that'd be y equals x, right? Y equals x would be 45 degrees. So 2x, is that one of our 16 standard trig angles? There are more angles than just those 16, right? Right, is it one of those or not? So is it 60 degrees? 2 to 1, right? So we're saying 2 to 1 ratio. Is that 60 degrees? It is not. Okay. Yep. You got it. Arctangent of 2, because tangent would be what? 2 over 1. Think about opposite over hypotenuse, or the rate of change. Tangent is basically the rate of change of your terminal side. That's a way to think of tangent. It's your rate of change of your terminal side. So then that theta is what he said, arctan of 2. So our limits are going to be, r goes from 0 to 5. And then theta goes from 0 to arctan of 2. Now we need, but then there's more to that. Okay, so that's the limits. That's good. That's the limits. And we know we're going to have dr d theta. But there's more going on here that we have to wrestle with. Okay, so we have to transform this whole thing into polar coordinates. And so you can't just use the function f of r and theta. It's not f of r and theta. It's going to be a different function based on how we transition, how we change variables from x, y to r and theta. So remember what x is? X is, remember, r cosine theta. Y is r sine theta. And what is r equal to in terms of x and y? That's another thing we'll need. Right, so this is all right triangle stuff, right? Is it x squared plus y squared? Not quite. Square root, right? So that's all based on the right triangle, right? With theta being here. This is x, and this is y, and this is r. So that's where all that stuff comes from. X is r cosine theta, y is r sine theta, x squared plus y squared equals r squared. All comes from that little construct right there, where this is our point, xy. This is 0, 0, right? This is the pole right here, pole. That's our point xy. And so based on that right triangle, we get all these relationships. That's review. So when we change this function of x and y, we have to transform it according to these relationships. But there's something else we have to take care of too. So we're not quite done. Question? Okay. Okay, but so we want to develop it. Okay. So so I mean, just saying that doesn't. We don't want to know why, right? So. Okay, questions on this little intro here. So I have a slicker slide here for you. So here's what we're talking about now. Polar, inside to outside, and then a starting theta counterclockwise to a final theta. So from inside, like closest to the pole, to outside, away. So inside to outside. And then from a starting theta to a final theta. They called it alpha and beta. I called it theta 1, theta 2. Same difference. Okay, so we know that the order is dr d theta. We just saw that in that little example we just did. The order is dr d theta, but what is dA? So what was dA before? What would dA be before in rectangular coordinates? How do we get a little bit of area? Yeah. dx dy or dy dx. It's just a little rectangle, right? It's just the area of a little rectangle. Base times height. But what is dA in polar coordinates? It's not. We're still going to use a rectangle, but now the rectangle is based on distance from the pole r and a change in theta. Okay, so let's label everything in here. So we got five things to label here. 5 things to label. So first of all, what is this right here? What angle measure? That's it's indicating an angle measure. So starting from the positive x-axis up to our point of interest would be theta, right? It would just be our angle measure. That's our angle measure. The measure swept counterclockwise from positive x-axis. Okay. And what would this be? This is a little chunk of area here. Then what angle measure is that? That's our d theta, right? That's our d theta. Okay, and then what's our distance out to our little tile here? That's just r, right? Okay, and then what's this right here for a tile? dr. Okay, so this is the angle measure d theta, but this is a length, right? This is a length from here to here. So how do you get the length, kind of like you can do a little arc length. How do you get the arc length formed by d theta, a distance of r away from the pole, right? So it can't be d theta because that length keeps growing as you go out further away. So we're going to use the formula for a circular arc. So what is that little arc length right there? And what is theta now? It's not r theta. So our angle is d theta. So this little thing is r d theta. So what is dA now? dA is not dr d theta, but instead r dr d theta. Why? Because d theta is not a length. D theta is a little change in angle. Depending on how far you away from the pole, your length is determined, right? So it's that little length. It matters how far away you are, right? Down here, that little length is short, but out here, that little length is a lot bigger. And so our arc length formula is radius times angle measure, and that gives us that little arc length right there. So we need r. But the order is dr d theta. So, but r d theta gives us that dimension, and then times dr gives us dA. So whenever you set up or you change from rectangular to polar, dx dy or dy dx becomes r dr d theta. Got to have that r. And so then what happens to the r? The r then latches on with your integrand, becomes part of what your antiderivative. So it enters the picture through dA, but then it grabs onto whatever the function turns out to be. It's going to be a function of what? R and theta. So you get an extra r in your function. Does that make sense? So it comes to the table with dA, but then you're going to have some, function of r and theta times r dr d theta. And now when you do the antiderivative, you got to include that extra r with your antiderivative. Does it make sense? Okay, questions on just the basics here, the underlying premise of a polar double integral. So you got to know your angles. You got to know your trig in order to set these up. So we'll practice with some. I'll give you some regions here, and you're going to write the limits. Okay, you do all these on your sheet. These are all for your sheet. Any questions? Can I erase? Can I go on? Anybody have a question? Last chance. Going once. Gone. I told you I'm a tough auctioneer. Okay. Here we go. So we'll call these A, B, C, and D. And so you're going to write just the limits of integration, right? So for each one, you're writing r goes from what to what? And then theta. So it's r first, that's the inside integral. So r from what to what? And that's like inside to outside. And then from starting angle, counterclockwise to finishing angle, right? So in that, what do we have in that other example? We had what? It's from 0 to 5 and 0 to arctan of 2. Let's just draw that region again. So that's what you're doing. So then you could just write, F, and we'll do dA. Just FDA is fine. And we don't care what F is right now. We're just working on the limits. And so what was that region? That was from 0 to 5. And then from 0 to that was that whole thing, right? Can you see those grid lines are 1, 2, 3. Can you see them? This is 1. It's the same for all of them. Do the grid lines show up, especially in the back? Can you see them well enough? Okay. So all the angles that you need are multiples of pi over 4. They're all based on the angles that splits the quadrant, right? So they're all multiples of pi over 4. Is the task clear? Okay, you're either making progress or you're getting help. You got 2 minutes. See, is that a good one to do? Okay, so for C, R goes from what? So our angle is from here to here. R goes from what to what?
0 to 2.
Someone said 0 to 2. Yeah, so we're starting at the pole, so we want to start at 0, and then we always end at R equals 2. So 0 to 2 in R, and then theta goes from? Starting angle will be this way, that's pi. Finishing angle will be 7 pi over 4. So 0 to 2 and pi to 7 pi over 4. Okay, do those regions make sense? Okay, so let's do something a little more challenging here. Okay, so here we got one. This is this type 1, type 2, or polar? Am I giving you type 1, type 2, or polar? Type 1, bottom to top, left to right. Okay, so this is very manageable. This is right along with the examples we had earlier. This isn't any harder. Okay, it just has a kind of a little bit of an ugly function. But we want to sketch this region first and foremost. Given a double integral, always sketch the region. These are geometry problems. These are geometry problems. You're not going to be able to twist these functions around in your head and change the order of integration. You have to draw the picture and then start over. Draw the picture and then start over. Don't try to say, don't try to wing it by looking at the formulas. Make a picture, start over, and recreate the double integral that you want from your picture. That's the way to approach these. All right? So we want to change the order. So notice that if we were to do this with dy dx, what would we have to integrate with respect to first? Y. Okay? And that's nasty, he said. Well put. Okay? Yeah, so with respect to it. So we're going to change the order to dx dy and solve, and then we're going to change the integral to polar and solve. But let's see how much we can do of this in class. So let's do number 1 and number 3, and then we can do number 2 later. I want to see if we can get that integral changed to polar coordinates. So sketch the region, change to polar coordinates, and see how far we can get solving that. Once you get the region, good. And then we're going to change it to a polar integral now. So what does that mean? dy dx becomes what in polar integral? dr d theta, right? R dr d theta. dA, this is our dA. It's got an R with it. R dr d theta. Okay? So then that R is going to latch on to whatever this becomes. It's going to be part of our antiderivative. That R ends up with a function. So it comes along with the dA, and then it joins up with a function, the R. Okay? X equals R cosine. So we got an R, we got an R cosine, and what's the denominator? Just R, right? That's just R. So then you can do it. No, it's in polar, this particular function is a lot easier. And what do we get for the limits? R goes from 0 to 4. Theta goes from? So 0 to 4, and then the pi over 2 to 3 pi over 2. Well, it's the whole left disk, right? Left disk. Okay, and then we got what? R cosine theta over R times R dr d theta. Yeah, definitely. Yeah, the R, all algebra rules that you've learned in the past apply. Okay, so if you have R over R, that's 1. Okay, antiderivative first with respect to R will be. So this morning I was doing it both the number 2 way and number 3 way, and I couldn't get the numbers to agree. So I'm either making a mistake with this or with the type type 2. So see if we can fix my mistake. All right. So with respect to R, antiderivative is. No, antiderivative. Antiderivative. R squared over 2 cosine theta, right? And that's going to be from, R goes from 0 to 4. And we're plugging the 0 and the 4 in for which variable? This is R. This is our R, right? So we got pi over 2, 3 pi over 2. So 8 cosine theta minus 0, right? 16 divided by 2 is 8. Is that right? 8 cosine theta d theta. Are we good? Now, antiderivative of 8 cosine theta is? Positive, right? 8 sine theta, and that's going to evaluate from? Sine of 3 pi over 2. Negative 1. That's the bottom of the circle, right? Y coordinate's negative 1, so we're going to get negative 8 minus 8 times sine of pi over 2. So we get negative 16. My mistake must have been in this one. So this is what I'm going to leave to you. So here's the deal. I need your homework, and remember.